Alright, welcome back. This is lesson 22.2, one of my favorite lessons in the entire Algebra 1 curriculum. So, our goal for today is going to be interpret the parameters of linear exponential functions in terms of a context. So just like last time, we're interpreting exponential functions, and we are going to move on to exponential decay. I love exponential decay. And so in our books, they're going to talk about the most common exponential decay question, which is radioactive decay. And I'm a nerd, so I think it's really awesome, but y'all are not as nerdy as I am. And so most of y'all think that it's boring. So instead, we're going to push a tire down the side of a mountain. So I have a link here. Your teacher should provide you that link. If not, you can read it. I'll give you a minute. I'll let it sit here for a second so that you can type it into your browser, and you can watch this tire bouncing down the side of a mountain. It sounds boring, but trust me, watch the video. It's awesome. So again, you're going to go to this YouTube video. I'm leaving it here on purpose for a minute so that you can type it in if your teacher has not provided you that link. And so it's https ://youtube.be/m-xkyuc 08 capital U capital Y. Alright, at this point you can just pause the video if you really need more time to put that URL in. Watch the video, watch the tire bounce, and then when you're done watching it, come back to this. So, we're going to oversimplify it. If you look on page 330 in your Springboard book, they did radioactive decay, which most of my students find super boring, so they like the tire better. So we're going to use the same graph. It's just got different axes names. So every time the tire bounces down the mountain, it lost half of its height from the top of the mountain. And so you saw like the first bounce, it went really high, and then the second bounce, it wasn't quite as high, and the third bounce it got lower and lower and lower until it just stopped rolling. So we're going to use the same graph on page 330 that represents radioactive decay, but I don't want you to think about it as radioactive decay. I want you to think about it as how high did that tire bounce every time it hit the ground. And so it bounced really high the first time, lower, lower, lower. It's still the same thing. It's still exponential decay. And I want to remind you that the exponential function is f of x equals a times b to the power of x, where a is your initial value, b is your common ratio, x is the input, f of x is the output, and again, from yesterday, f of x is the same thing as y in Algebra 1. Algebra 1 only. In Algebra 2, that's not always true. So f of x is y in Algebra 1. So let's take a look. So based on the graph that we have of our tire bouncing down the side of the mountain, we can establish a few things. So the first thing is, what is the initial value? So if we look at our graph, when we say initial value, how far have you moved when it's the initial value? And the answer to that is you haven't. You haven't moved at all, right? So if our initial value is when we haven't moved, then we're going to look at the x value when it's 0. And when x is 0, how tall, how far up the mountain was that tire? And the answer to that is 400 feet. It was 400 feet in the air. Then the question is, what is the common ratio? So some of you will be able to visually look at this and see what's happening, and some of you will not. And the key, if you want to look at it visually, is how did it change from the first bounce to the second bounce, and how did it change from the second bounce to the third bounce? Visually, there's a clue there. But if you're not sure, do what we did yesterday. Make a sequence of all of your outputs. We went from, I'm going to do it up here, we went from 400 to 200 to 100 to 50 to 25, and we stopped graphing it at that point. It would continue to reduce at the same rate. We know this is geometric, so we know we're either multiplying or dividing. So what can I multiply 400 by to get 200? If it's easier to think about division, you can say, what did I divide it by? And so we divided by 2. We divided by 2. We divided by 2. This tire bounce was halving each time. So when we say it was halving, or when we say divided by 2, another way to say division in terms of multiplication is to multiply by 1/2. We're halving it. We're multiplying by 1/2. So the common ratio of this is 1/2. Well, if we know the initial value and we know the common ratio, we know the formula, because the formula is f of x equals a times b to the power of x. A is initial value, so f of x equals 400. B is the common ratio, and we get f of x equals 400 times 1/2 to the power of x. And we have our exponential function, which is great because now we can answer all kinds of questions about this. So we can say how far is off the ground is the tire after 4 bounces. And you know, if you have that graph available, that's an easy question. But it's not always going to be available. You have to be able to read your equation to figure that out. So we have f of x equals 400 times 1/2 to the power of x. And we want to know how far is it after it bounces 4 times. So the question is that 4 bounces an input or an output? If we want to know how far it went after 4 bounces, the 4 bounces is not the result, right? The 4 bounces is what caused the result. So we are going to say that that is an input. And which variable is input? In this case, it's x, or in every case, it's x, right? So we're going to say that this is f of x equals 400 times 1/2 to the power of 4. And don't freak out. I know most of you are going to use your calculator, but please stop using your calculator. You can do this math. 1/2 to the power of 4 is 1/2 times 1/2 times 1/2 times 1/2. And how do you multiply fractions? All the tops multiplied together give you the top. All the bottoms multiplied together give you the bottom. 1 times 1 times 1 times 1 is 1. 2 times 2 times 2 times 2, that's 4, 8, 16 is 1/16. So this is the same thing as 400 times 1/16. And again, I know that you don't like this. Nobody likes it. But you need to get good at it. Stop putting it in a calculator. We have 400 times 1/16. We really don't like to multiply whole numbers by fractions, so we turn those whole numbers into fractions. Multiply top times top, bottom times bottom. We get 400 divided by 16. So 400 times 1/16 is the same thing as 400 divided by 16, which again is 5th grade math. If you could do it in 5th grade, stop trying to avoid it in high school. So we have 400 divided by 16. How many times will 16 go into 4? Well, it won't. So we have to move on to 40. How many times will 16 go into 40? And that's twice. That's 32. We get 80. How many times will 16 go into 80? Well, if it went into 40 twice, we know it's going to happen at least 4 times, right? But maybe it's 5. So let's say 16 times 4 is 6, 12, 24. That's 64. 16 times 5, that's 0, 3, 8. Oh, and it's perfect. So we get 5. And 16 goes into 400 exactly 25 times. So the question is, how far off the ground will the tire bounce after 4 bounces? And the answer is 25 feet. The tire will bounce 25 feet on the 4th bounce. We did it all with 5th grade math. If you could do it in 5th grade, you can do it in high school. So we could ask the same question backwards, though. How many bounces does it take for the tire to have a bounce height of 25 feet? We have the same equation, but this time we're given an output, not an input. We know that the result is going to be 25 feet, so we can replace f of x with 25. And then we just have to start getting things by themselves. Divide by 400. And we get 25 over 400. What can both of those be divided by? And that's 25, right? Because this is something that's this is a multiple of 100, so clearly 25 can divide it. So if 25 goes into 100 4 times, it would go into 400 16 times. So we can say 1/16 equals 1/2 to the power of x. So now we just need to figure out how many times do I need to take 1/2 times itself to get to 1/16. So this is to the first power. 1/2 to the first power is 1/2. To the second power is 1/4. To the third power is 1/8. To the fourth power is 1/16. So in this case, x is 4, and we know that it takes 4 bounces of that tire to get to 25 feet. It's weird, but it's not difficult. You just have to practice it. So let's look at yesterday's exponential function versus today's exponential function. And the question is, what was different? And just as a reminder, yesterday we were talking about houses and their values going up. And when we graphed them, we did several graphs, but when we graphed them, they ended up looking something like that. And today we talked about this tire bouncing down the side of a mountain, and when we graphed it, it looks something like this. So the question is, what is different? And it actually doesn't look like that at all. I just can't draw. It looks like this, right? So the question is, what is different? And the answer should be kind of obvious visually. Here, the values are going up. Here, the values are going down. And the question becomes, can I just look at the equation and know that it's going to be decay? So if we think about some of our equations from yesterday. So yesterday we had f of x equals 10,000 times 2 to the power of x. Another one yesterday was f of x equals 10,000 times, I believe, 1.5 to the power of x. I could be off. Today, our equation that we just made was f of x equals 400 times 1/2 to the power of x. And so some of this is going to be just, can you visually see a difference between these, which are growth, they're getting bigger, and these, which are decay, or this one, which is decay, it's getting smaller. What's different about these? What is going on? Why might these be growth, and why might this one be decay? Look at these, try and figure it out, and we're going to do some examples and see if you can figure it out as I go along. So the question here is going to be, are these examples of growth or decay? So the first one is 10,000 times 2 to the power of x, which was yesterday's equation, and it is growth. So keep trying these and see if maybe you figured out the answer. If you haven't, I'm going to go over why they're right or wrong in just a second. So the second one is 1/2 times 2 to the power of x. Is this growth or is it decay? And this might surprise some of you, but this one is growth. So some of you may have seen it was growth, some of you may have just guessed it was growth, but some of you might have thought it was decay, and you need to consider, why is it growth even though your brain kind of thought it might be decay? And we're going to go into it, but I just want you to chew on it. So here we have 47 times 3/7 to the power of x, and this guy is decay. This one is decay. And so some of you that said decay on the second one are probably now crying foul, saying, wait, no, I thought that it had to be growth because you just said that one was growth. You're looking at something a little off. Look for the patterns. You'll see it. So in the fourth one, we have 1/2 times 3/4 to the power of x, and this one is also decay. And hopefully you're starting to spot what might be going on here, but maybe not. We'll talk about it. And in the final one, we have 1/2 times 6/3 to the power of x. And this is not obvious at all, right? Because probably you said it's decay, but this one is growth. So what is going on here? Why are these three growth and these two are decay? Because it's hard to look at this and like wrap your brain around what's going on. So I will tell you, with growth or decay, deciding if it's growth or decay, the A value, that initial value, is irrelevant. It doesn't matter what the A value is. We don't care. Might as well not be there for the purpose of deciding is it growth or decay. It could be a fraction, it could be a whole number, it could be a decimal, it could be an irrational number. It really doesn't matter what the A value is. Growth or decay is determined by the B value. And you'll see that in my 3 growth functions, all 3 of them, and I didn't mean for them to all be 2, but all 3 of them are bigger than 1. They're bigger than 1. So 2 is bigger than 1, it's growth. 2 is bigger than 1, it's growth. 6/3, which is 2, but it could have been 5/3 and it'd still be bigger than 1. So let's pretend that that was 5/3 the whole time, even though it wasn't. So if it was 5/3 the whole time, that's still bigger than 1. It has nothing to do with is it a fraction. Please get that in your head. It is not is it a fraction. Is it bigger than 1? 5/3 is bigger than 1, so this is growth. Then here in these 2 decay questions, 3/7 is smaller than 1 and 3/4 is smaller than 1. So it is decay. You need to be able to identify, are you looking at growth or decay? So your teacher is going to have some practice problems for you. You need to make sure you get good at this. Don't put it off and assume it's easy. Don't put it off and assume you'll get it later. Work on it. Ask questions. Please, please, please ask questions.